The lecture kind of just fell apart because we started answering Java questions, and I got confused because I hadn't thought about it before I showed up, because all my Paradigm students were pestering me when I was supposed to be thinking about how to plan for class. So sorry for the bad lecture. We'll do better this time. But before we move on, I do want to give the people struggling with Java a chance to just ask questions. So those of you who are still struggling to get the next assignment in, what's Java doing to you? What do you need help with? Or are we okay and can we move on? It's okay if you have a question. Did we settle it last time, despite struggling a little bit with it? Okay. I'm going to assume that we're all done with the assignment. Java's in the bag. We get how to work with Java now, and we're going to move forward and work on the next assignment. If that's not true, come see me, post on the forum, or raise your hand now.
So, I just had a question.
Okay, thank you.
It wasn't a question about how to use Java. It was more of a question on the assignment in general.
Okay.
You said that you coded up yourself in C++, but you asked us to do it in, or you gave us the code to do it in Java.
Right.
Why was that?
So last time I taught this class, I thought I was going to be all language agnostic. Everyone can use whatever language they want. And I'm still kind of that way. If you want to use C++, that's fine. But then halfway through the semester, I got this great idea of doing an AI tournament. And I had to write it in some language. And I realized that half the class would panic if I used anything other than Java. So I used Java to write that. And I think I want to do that again this semester. And so it occurred to me that you're all eventually going to do something in Java. So if we just do everything in Java, then there's consistency. That's the reason.
Okay.
If you're one of those Python programmers who loves teaching yourself languages, please use Python. That's great. I'm happy with that. But we're going to do Java in some of the assignments, and you'll be stuck with it. So there. Okay. So here we are. We actually recorded last time's lecture, but I haven't posted it yet. I'm actually a little torn as to whether I want to, but I will get to that right after class. I'll post that up there in case you didn't see that. And I think we're recording now. Moving on, assignment 3. I've talked you through this a little bit. Let's see. So here's this problem. You've got a puzzle, and you need to solve the puzzle. If you really want to, you could print this on a piece of paper and cut out the shapes, and you could do it by hand. If you really want to, you could code it up and make a mouse interface and sit there and try to solve it using software. I haven't coded that up for you yet, although I've done most of it. If you scroll down here, there it is. So here's some code. It basically displays this board. And instead of having a nice click to move interface, I just have a click and it makes a random move. And it doesn't even check if they're legal moves, it just moves. So it's really bad implementation, but I've done most of it for you. If anybody wants to turn it into a game, cool, you can do it. But you don't have to. Has anybody ever looked at this puzzle and maybe tried to solve it?
I think I've seen it in that.
Have you played Professor Layton?
Yes, I have.
That's,
No, I think
so I ripped this off of Professor Layton.
Which Professor Layton?
I don't even
First or
remember.
second one?
Whichever one my wife was playing about 2 years ago when I first designed this class. No, 1 year ago.
Okay, it's the more recent one then, so yeah, I haven't seen this.
I think it was something about a ghost.
Yeah, I haven't played that one. I played the older one.
Okay, well, there's a puzzle, looks like this in it. Except in that one, the top opening opens, you can move the red one out. But if you try it, it's hard. Move the pieces around. You gotta do a lot of shuffling and sliding back to get that red thing out of there. And there's just not a lot of space to work with, and it's actually quite a pain. But it turns out it's solvable. And I know this because we eventually solved it. And then I coded it up and solved it way faster than I could have by hand. And now I'm making you do it. Now, if you've already got uniform cost search working, which you all do, this is going to be a really easy problem. The only thing you have to do is represent the new problem. And really, it's that easy. Unless you didn't really do the previous assignment very well, in which case you'll have to clean it up. And that's deliberate because now I'm forcing you to have done the previous assignment really well to solve this one. So I know that's kind of mean, but frankly, I think it's the right thing to do because now you will have really understood uniform cost search by the time we're done with this assignment. Now let's talk a little bit about how to do that. How is this uniform cost search? How are we getting, where are we going from and where are we going to? Can you even fathom that? We're going from right here, this whole thing, to some state where this red block is right up there. Where we are, this point, is actually the whole puzzle. Now that's not a 2D point, it's a what? How many dimensions do you need to express this puzzle?
22.
Yeah, so I've already talked a little about that. Why 22?
There are 2 different dimensions that each piece can do that.
Yeah, there are 11 pieces. I even numbered them, 0 through 10. By the way, that number is not significant. I just numbered them because I thought maybe we need to talk about it, and if we could just say piece number 10, now we're all on the same page. There's no meaning, you don't have to in your code make this be piece number 1, but why not? Then we'll all be the same. If we all do it the same, then it'll be even easier for me to debug all of your code when you come to me for help, right? So I just arbitrarily assign numbers to it. Okay, so you have an array of 22 values, 0 through 11 times 2. There's an x position and a y position. How is 22 values a point? Have you got that through your head yet, that 22 values can be a point? Or does that still feel like 22 points to you? Or does this feel like 11 points? How many points is that?
So why don't we have to concern ourselves with the shape of the blocks?
Well, your code will concern yourself with the shape of the blocks. So don't misinterpret that. I'm not saying the shape is unimportant. But I am saying the shape is unimportant for specifying, for uniquely identifying one configuration from another. Because no matter what state the board is in, suppose I start here and I move this piece up and that piece over and this piece down and that piece over and this piece over. What is the shape of this red one? Square. Now suppose I move this piece over and that piece down and that piece over. Now what's the shape of the red one? Square. You could tell me this piece is here and that piece is there and this piece is there and the red one is a square every time, no matter what happened, but you would be supplying me with no new information because you would always say and the red piece is a square. So you don't really need to tell me it's a square when you're telling me the state of the board, but you do need to tell me that it's a square when you're describing the puzzle to me, right? So if we were in a dark room and you had never seen this puzzle before, and I told you the state is 2, 4, 8, 13, 12, 6, 4, whatever, that would be absolutely meaningless to you because you have no context whatsoever. So the shape of these pieces is part of the context, part of the meaning, the problem, however you want to state it, but it's not part of the unique configurations that it can take. So having defined that, I want to be very clear that when I say the word state, what I mean is a minimal description of the way it is, of its current configuration. I don't want you to describe to me what problem I'm trying to solve. I don't want you to tell me how many boats are currently trying to cross the Pacific Ocean, or the price of Microsoft stock currently, and those things are not important to the state of the puzzle, nor is the shape or the color or all those things. Those are just parts of the universe, so to speak. So I'm going to call the shape context, or the problem perhaps, and I'll call state this vector of 22 values. Okay. Now I mentioned before, if you had 22-dimensional space, if you have 2-dimensional space, how many axes do you have? 2. Horizontal axis, vertical axis usually. That is if it's a Cartesian coordinate system or a Euclidean space. But if you have 3-dimensional space, 1, 2, 3, usually. Well, why those directions?
They're orthogonal.
They're orthogonal, yeah, and that's this. Apparently, the physical universe in which we live has 3 orthogonal directions, and so we can map between 3 numbers and space very easily in our heads. Our heads are used to 3 dimensions, because there are 3 dimensions all around us. But kind of a dimension is just one of these axes, right? And you can plot whatever the heck you want on axes. Don't you agree? Suppose I have some axes and I want to plot your age on this axis and your height on this axis. I'll get a scatter plot of a bunch of points. You can't tell me I can't do that, right? So I can plot your age. I can call your age a dimension if I want to. Is age a dimension? So have you ever watched one of these old bad horror movies and they talk about coming through the 5th dimension or something like that? Or, we're going to travel into the 6th dimension. What does that mean?
Means the directors don't know anything about science.
Yeah, it means the directors don't know anything about science, because if the 6th dimension were a thing, that would mean there's a direction you can go that nobody else can go. And maybe there is. Maybe there is another direction. Like, here, wait just a minute, then pretend I disappeared. Then I come back. I just passed through the 6th dimension, right? I guess that's the way it would be, because we're at some location in the 6th dimension, and the 3 dimensions we know about are all orthogonal to that dimension. So you can imagine we're all at the same point, and if I went to another point in the 6th dimension, you wouldn't see me for a while until I came back. That's all weird and trippy, but here's a few things that are off. The 6th dimension would be continuous, presumably, because 1, 2, and 3 are all continuous. So if it were continuous, you can't go to the 6th dimension, you go through the 6th dimension, right? Okay, has anybody seen the movie Flatland? Okay, homework assignment, ungraded homework assignment, but you really should. This is really cool. Google for Flatland.
It's really short too.
Okay, there's a YouTube about it, there's a book. Familiarize yourself with Flatland because it'll make you feel trippy and weird and it's kind of cool. But basically, Flatland is the story of a square and he wanders around in Flatland because it's 2-dimensional. And he suddenly discovers the 3rd dimension and it's all about philosophizing about what extra dimensions mean. And I probably didn't even describe it very well. But watch Flatland, it's a really weird YouTube, and all of a sudden you'll understand dimensions better. Okay. All a dimension is a number. As I was saying, I can plot my age on a dimension, I can plot height on a dimension. Can I plot my weight? Sure. Can I plot the amount of oxygen in my blood? The amount of alcohol in my blood? I don't drink, it's going to be very low. But I do eat bread, and bread contains alcohol, which, so there's got to be some in there. So a dimension really is whatever the heck we want it to be. It's just anything we want to measure. So in this case, there's 22 dimensions because it takes 22 numbers to describe the state of this puzzle. And that's it. A dimension doesn't have to be a woo thing, or you don't have to pass through it and become a weird zombie. It's just a number. It just takes 22 numbers to describe this thing. That's all a dimension is. But if somehow we had 22 orthogonal axes in some Euclidean coordinate space, then a single point in this 22-dimensional space would describe this puzzle. Now here's something kind of weird to think about. Suppose we take this puzzle and we move just one piece. How has the state changed?
Moved along that axis.
It's at least pretty close to what it used to be. Only one of the numbers has changed, and most of them haven't. So in 22-dimensional space, if this point represented that puzzle, this point next to it, along one of those 22 axes, is different and all the rest are the same, is the puzzle where we've moved the piece a little bit, right? Well, if we moved the pieces all around and generated all the points that represent that, there'd be these points scattered through 22-dimensional space, and kind of weirdly, they wouldn't make a perfect square, they would make some kind of shape. And I can't even tell you what shape it would be because it's 22-dimensional space, and I can't see 22 dimensions. All I can do is print out lists of 22 numbers. And in fact, you'll do that. So this is kind of what the output of your assignment's going to look like. It's a bunch of numbers. And you can't possibly visualize it because there's no way. But if you could, somehow this would be a shape in, or rather a path, winding away like a little snake snaking around through 22-dimensional space, getting from starting point to an ending point. Does that make, is that too trippy, or is it good enough, that, or is it just yawn, that's kind of mathematically obvious type thing?
So we've got a window into the 22nd dimension right here.
Yeah, I mean, I can't really plot this, but if I could, this is a path. At the very start, all zeros. The next one is something almost all zeros, except that one's a 1. The next one, same as the previous one, except one of those numbers changed. I'm going from a point to a next to it point, 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 and each time I'm going next to it in a new dimension. This time we pass through the first dimension. This time we pass through the 1, 2, 3, 2, 4, 6, 8, 10, 12, 14, 16, 18, the 20th dimension. We passed through the 20th dimension. It's exciting. You're going to pass through the 20th dimension in this assignment. In fact, through all 22 dimensions. And you're going to pass through all these dimensions as you're going from some point to some other point, and that's the path. Some path from the start to the end is optimal, right? And whatever that is the solution to this puzzle. So you're going to start here at this point, because this is a point in 22-dimensional space, and you'll search through 22-dimensional space to find the goal, and when you do, you'll report the optimal path, and it will look kind of like that. So at least at a high level, can you wrap your head around what I'm asking you to do in this assignment? It's basically use uniform cost search to solve this puzzle, and it's not really any different than the previous one. Yeah?
Okay, so each one of those is the steps that you would move the piece in, right? Is that what you're saying?
Yeah.
So the
So-
output's going to be, if we were to tell you, move this piece, they would be the steps that you would take, is what you're saying.
Yeah. If this were your answer to assignment 2, we could just take, say, this column and say that's the answer. You have an x position and a y position, x, y, x, y, x, y, x, y, x, y. And you would describe, you go here and you loop up over there and you come down here and you go down and then you get to the goal. That's about what the answer was, right? So you'd have a big list of x, y points. You're here, then 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 here. Do you even know what I'm talking about? I have to go back to the train map, or we got it? Okay.
Yeah, I mean,
Yeah, it's just passing through points. Well, this whole row is 1 point. And this is the next point, and this is the next point, and this is the next point. So this is a path. What you're seeing right here is the red line. Behold the red line. And all these numbers produces the path. If you come down here and take my visualizing code, and you plug in those numbers into this code, in fact, let me show you where. Right here, I have this thing called byte state. Because state bytes. That state represents the board. If you plug in row 0 and visualize this thing, or rather, if the state is set to all zeros, it will produce a picture on your screen that looks just like this. And if you set that state to row 1, one of those pieces will have moved a little bit. So basically, run your answer through this visualizer, and you will see, graphically, this puzzle. The pieces will move themselves, and it'll go and it'll get this red block around here and out and finish it up. So you've got a graphical visualization of the puzzle solving itself by the time this assignment is done. Yeah?
So the assignment specifically says the black pieces can't move, can the white
Correct.
pieces move? They're not numbered.
I
Are these-
is this a white piece?
That's what I was thinking of. the black
Yeah,
piece.
this is background area, so that's not a piece. Of course, what's a
You can move
piece?
a piece into that, right?
What, say what?
You can move a piece in there, right?
Yes,
That one.
you may move this blue one to the right because there's nothing here.
Okay.
I made it the same color as the background of the webpage so
Yeah, I
that,
saw that.
so that it would feel like background.
So they can move into the empty spaces and they cannot move into the black.
Yeah, the blue one can move to the right. Number 3, number 9 can move to the right. It cannot move left because it would step on this black one. It cannot move up because it would step on this orange one. It cannot move down because it would step on 6 and 7. But it can move to the right.
And 0 can't go to the left.
0 cannot move right now.
Okay.
And that black.
In order to move 0, you're gonna have to move all these around and move them until there's some space there, and then you can move 0.
Okay.
So that black one kind of in the middle of the board is fixed. It's
Yeah,
like
this is a
border as
brick
well.
wall, this is cemented down to the ground, and it cannot be moved, because it doesn't have a number.
I'm pretty sure a big sledgehammer would make that puzzle a lot simpler.
A sledgehammer would make this puzzle a lot simpler. Unfortunately, the puzzle doesn't accommodate sledgehammers, so, yeah. The real world is better for these types of problems than virtual world. Yes, that's the problem. Okay. Yeah, you really gotta understand how to do the puzzle before you can possibly code it up. So let's really make sure you got it. You get how you do it now? What's the goal? To get this to there, right? Okay. And because black's in the way, you can't ever get these pieces out of there. You can't make number 8 disappear. That would make it really easy. Make them all disappear except the red one and then move it around. The whole reason this is hard is because everything's in your way. And that means you're gonna have to move things up and down and back and right and left and right. And ultimately, the path through 22-dimensional space is very snaky and bendy and windy.
What's the optimal number of moves?
Don't know. We did it last semester, so the whole class knew at one point. I could go dig up the previous implementation and find out for you. But basically, you already know your code is optimal. So as soon as you get an answer, it's right. That's how it should be. If you really want to know it's right, the way to do it is go down to that visualizing code and visualize it. I wrote that so you would visualize it. Those of you who don't, you're bums. I'm not assigning you to, but you really should visualize. If you're going to take the time to do this assignment, visualize the darn thing, because it's cool. And I already wrote the code to do it for you. And yeah. Actually, another student wrote the code to do it for you. I cleaned up the code. There's always some student in the class that makes every assignment cooler. And by the way, if you want to be that student, you are welcome to clean up my assignments. So if you get to the end of some assignment and you realize, this would have been so much easier if the wording on number 4 would have just been blah. Please fix my wording, email it to me, and I will benefit the next generation with your improvements. Okay. So, there's a problem.
I actually have a question about the solution to the problem.
Yes.
It says move the red piece to a position adjacent to the top. Does it have to be where piece number 10 currently is? Or can it just be on the top?
So, kind of I'm going to tell you it doesn't matter because
Oh, yeah.
there's no way you can get there without getting there first.
Right.
And so, let's just say it has to go there because that's the first one you'll encounter. And if you go over here, then you'll add 2 extra moves to your solution, and then the grader will think you did it wrong. So I'm going to just say for now, it has to be right there. Of course, what does right there mean? This one only has 3 squares, and this one occupies 4. What I mean is the top left corner of the red one is where the top left corner of the orange one is. It'll also occupy this blue spot there. Yeah.
How do you tell like collision detection? Like how do you tell if you have moved like out of bounds or if you just can't move that way because there's a black piece there?
Okay, excellent question. So, I'm in my uniform cost search algorithm, and I'm in some state, we'll say this one, because I have it right there. Here I am in this state, and I'm now asking, I have to iterate over all possible actions. In the previous one, there were 4 actions, right? North, south, east, west. How many possible actions are there here? I think we determined 44, right?
Well, that was 44.
I think it's 44, because each piece can move up or down or left or right, times 11. 4 times 11, 44. Okay, so there are 44 possible actions, and most of them are illegal. The question we're asking now is, of my 44, it's pretty easy to enumerate the 44 possible actions, right? Number 0 can go up, north, south, east, or west. Number 1 can go north, south, east, west. Number 2 can go north, south, east, west, etc. I have enumerated my 44 possible actions. Of those, which ones are legal? Well, piece 0, illegal, 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 illegal. Piece 1, illegal, 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 illegal. Piece 2, all illegal. Piece 3, all illegal. Piece 4, all illegal. Piece 5, all illegal. Piece 6, all illegal. Piece 7, piece 8, all illegal. Piece 9, all illegal except it can move east. Piece 10, it can move west. So there are 2 valid moves here. Do you all agree? Okay, so I did it intuitively. Now how do you do that in code is the real question you're trying to ask, right? Okay. I determined that intuitively. How would you determine in code that this one and that one are the only 2 legal moves in this project? Yeah.
I'd make a 2-dimensional array, then fill it up with characters, and if one tries to override another, then it's an invalid move.
Yeah, that's how I do it too. This could be a 2D array of bits if you want to be super efficient. Characters is probably easier in Java, so I'd just do bytes or whatever. You can do integers, it doesn't even matter. But make some kind of representation of this board. Don't do it graphically, like don't use a 500 by 500 pixel image and draw each piece, because then you're actually drawing a whole bunch of pixels and that's just slow. But if you had, say, notice how I numbered the squares for you, 0 through 9. It's actually a 10 by 10. So you need 100 chars, or 100 bytes. And the first thing I do is I write a little function that takes a 100 byte array, 2D array, or 10 by 10 2D array, and I fill in all the black ones, because we know those are stationary. And basically, well, first thing I do is I clear the array. I'd set them all to, say, spaces. And then I'd fill all the black ones in with the letter X, maybe, because X is a cool letter. Use your favorite letter. Then I'd run through all 11 pieces. Here's piece 0. I'd take its XY location. I'd draw its 4 parts in the grid. And if one of them was already an X, I'd say, hey, you moved onto a black space. Bad. Return false, basically. If I managed to mark them all X and they were all spaces before, I'd move on to piece 1. And then I'd draw it, piece 2, and piece 3, and piece 4. And if I succeed at drawing all 11 pieces into my 2D array without putting an X on top of an X, then it's a valid board piece. And if I don't, it's an invalid board piece.
So, with the 2D array, is there any, how would we build up the initial state of it, besides just like doing it by hand?
Ah, I have no idea how I would do it by hand.
Okay.
By which I mean, word to the wise, I had to do it in order to draw this visualization code. So look at what I did for you. Where did I do it? I wrote a method named shape. And in shape, I give it a shape number and an RGB value and coordinates of the 3 pieces that make up the shape. Basically, this is the information you need to rip off and stick in your code to not have to do it by hand.